Hello, I'm Owen Dowling.
I'm Connor Thompson.
I'm Conor Galera.
And this is Sparse Multichannel Multikernel Convolution, our submission.
So for strategies for parallelism, we first tried to delete this nested for loop because we assumed that it would just pre-initialize everything to 0 anyway. But when we did this, we didn't actually gain any performance increase in time. So we assume that the compiler is just automatically assigning everything to 0 anyway if this loop isn't present. So after that, we tried doing a pragma OMP parallel for collapse 3, and this only caused marginal gains in performance time at the right input parameters. So we had to figure out when to actually use parallelism.
So originally for the main portion of the function, we had it done twice. So once was in the way that Professor David Gregg had done it, because we realized that this was more efficient for smaller input sizes. And then the latter version of the function was done in a way that it kind of suited larger input sizes. And then at the start of the function, there'd be a if loop, that chose between these two versions. But we realized that there is something kind of that suited this within the library, and that was the OMP set number of threads function. So essentially what we did was that at the start of the function, we just multiplied a number of dimensions together and saw if this was smaller than a given constant that we kind of tweaked to the to a point, a sweet point, I suppose. We call this the Gregg limit. And so we use this piece of code here you can see on the slide.
Okay, so now I'd like to talk about approaches for parallelism that we found weren't approachable, for lack of better words. So what springs to mind is the nested for loops that comprise the multi-channel multi-kernel convolution part of the function. So in that instance, our immediate thought was, okay, if we make clever use of this sum variable, which is present in the code, and move the output assignment outside, this would be a classic case where you can apply a parallel for reduction operation or strategy from the OpenMP library. And we expected this to be a marginal or massive boost to the performance. But what ended up happening is that we just encountered again and again segmentation faults. So a segmentation fault is an error which occurs essentially when you try to access memory addresses which are illegal memory addresses. So what I understand what's happening there is that we parallelizing these for loops is causing all sorts of different memory indexes, and these indices are ending up in some capacity to indexing each other. So really we have a very complicated problem in which we need to introduce locking mechanisms, and due to the complexity of that problem, we decided it was smarter to just not go ahead than with parallelism in this section of the code, as opposed to trying to figure out a locking strategy in the time we had. And other approaches we attempted for parallelism didn't improve the performance in the slightest. So what worked out better instead is if we use the vectorization technique in this section of the code. And it turns out that this wasn't necessarily straightforward, because we had a variable called this C, which was an index of another array, or a value taken from the index of another array, and that's itself an index to another array. So what you're trying to do there is you're trying to index non-contiguous blocks of memory. And to achieve that, you would typically want something which is a sparse linear algebra operation the sort of thing you would want in a sparse multi-channel convolution, perhaps, called gather-scatter. And gather-scatter is not supported by Intel's SSE4 intrinsics. So what we did instead, and this was our workaround, we introduced a tiny for loop of size 4. And what we're doing is we're getting these indices in a scalar fashion and loading them into a float array of size 4. And then we can proceed with that and create a vector of the images as we see there. And likewise, we have a value vector, but it was the image vector is what we were worried about here. And the sum vector, I mean, we multiply the values in the image vector and the value vector. And by applying 2 horizontal add operations, we end up with a M128 vector of which can be considered 4 32-bit floats, and each of the 32-bit floats is the sum attained by adding all 4 of those together.
Another problem that we had to handle while we were working on this project was how unpredictable the performance on Stoker could be. So we were testing our code at all different times of the day, and we found that there were often performance spikes which gave us some outrageous times for the input sizes that we were using. And as an example, on the screenshot that's on the slide, you can see I ran the original code with the smallest input sizes possible, and I got an initial time of 183 microseconds. And immediately afterwards, I ran it again with the same parameters, and I got a time of over 2000 microseconds. So it was something that we had to bear in mind when we were trying to figure out the average running time for code during the project.
So here you can see the mean run times for our code versus the original code. So our optimized code outperformed the original code for most 75% of the input parameters we tested. The rest of the time, our code had near identical performance.
Okay, very good. That's